Now here is an important characterization of a square matrix. Particularly the principal diagonal of a matrix is valid only in a square matrix. In a square matrix, let us see what is the principal diagonal. The collection of elements Aij where I and j values are equal. That forms the principal diagonal. So when we consider a matrix A square matrix A of order 3 by 3, how will be the listing of the elements? Yes, it would have A11, A12, first row, second column, A13, A21, A22, A23. Then in the third row, first column, third row, second column, and third row, third column. Now in this, what are the elements which constitute the principal diagonal? The elements for which the row number and the column number are equal, that means A11, A22, A33, right? Now if you look at the marking there, that's forming the diagonal of the square which we are talking, right? Such a diagonal is called the principal diagonal. So what is the principal diagonal of A? Yes, that would consist of the elements A11, A22 and A33. If we consider a 2 by 2 matrix, how will be the elements entries in this? Yes, there will be 2 rows and 2 columns. Therefore, this is a square matrix having A12, A11, A12, A second row first column and second row second column. So what are the entries in the A22 where we have the row number and the column number are equal? Yes, A11 and A22, that is the diagonal of the square matrix 2 by 2. So for this, what is the principal diagonal? The principal diagonal of A in this case would consist of A11 and A22. Now if you look at both the examples, can we generalize the matrix as if A is a matrix having Aij entries, which is square matrix of order n by n, such that I and j both values would be running from 1 to n, then how will be the principal diagonal of A? It would consist of n elements, that is 1 1, A22, A33, so on up to the last row, last column, that means ANN. There will be n such entries in the principal diagonal of A. Now this principal diagonal of a matrix, square matrix, would give some more types of matrices. Let's see what are they. First is a diagonal matrix. Let us see what is a diagonal matrix. Diagonal matrix is a square matrix if Aij equal to 0 for all I not equal to j. That means whenever the row number and the column number are not equal, that element should be 0. That is a square matrix in which all the elements outside the principal domain are zeros is called a diagonal matrix. Let's consider a simple example to understand this. Now if you look at this matrix, which is 3 by 3 order, A1, A12, A13, A21, A22, A23, right? A31, A32 and A33. These are the entries of a 3 by 3 matrix. What are the elements in this which are satisfying I not equal to j? Yes, other than the principal diagonal, that means other than these elements. If all the rest of the elements, that is A12 where the row number is not equal to the column number, A13, 1 and 3 are not equal, therefore that is also 0. A23, row number and column number are not equal, therefore that is 0. A21, that is 0. A31 is 0. A32 is 0. Then how will be this matrix? When you write the entries with zeros at non-diagonal and the diagonal elements as it is, then this is A11, 0, 0, 0, A22, 0, 0, 0 and A33. Then except at the principal diagonal, all the elements, other elements are zeros. Then such a matrix is a diagonal matrix. A square matrix in which all the elements outside the principal diagonals are 0 is called a diagonal matrix. Now for a diagonal matrix, we have a very important notation. When all the other entries are 0, then the diagonal matrix is denoted by diagonal of A, and this can be expressed as a set of A11, A22 and A33. So diagonal matrix need not be expressed as a full form. Even this will be a shorter notation of a diagonal matrix A. In other words, suppose if I give you diagonal matrix of A is given by 3, 4, -1 and 1. Now, how many elements are there in the diagonal? The diagonal has 4 elements. Now, which square matrix will have 4 diagonal entries? Correct. The matrix A must be a 4 by 4 matrix. In a 4 by 4 matrix, all the entries other than the principal diagonal entries must be zeros. And in the principal diagonal, there should be 3, 4, -1 and 1 respectively. That means there should be 4 rows and 4 columns. So let us write the first row. It has 3 in the main element. Then the rest of the 3 elements are zeros. Similarly, in the second row with 2, 2 element should be 4 and the rest of the elements are zeros. Similarly, in the third row with third column, that means here the number must be -1 and other than this A33, rest of the element should be zeros. And in the fourth row and fourth column, that means at this corner there should be 1 and the rest of the element should be 0. This will be the matrix of order 4 by 4, which is denoted by diagonal of A, right? So diagonal matrix can be just expressed as a diagonal A given by these elements. Now when we generalize a matrix A, when we say diagonal of A is the collection of A11, A22, A32, A33, so on up to ANN. Then how will be the matrix expansion for this? Yes, let us see first how many elements are there in the diagonal. There are n elements in the diagonal. That means the matrix A must be of a square matrix of order n by n. Then there should be n rows and n columns, in which the first row, first column element must be 1, 1. The second row, second column element must be 2, 2. The third row, third column entry must be 3, 3. So on up to the nth row, nth column element must be ANN. And the rest of all elements must be zeros. That means the element at 1, 2, the element at 1, 3, the element at 1, 4, so on up to the element at 1, n must be 0. Similarly, the element at A21 should also be 0. The element at 2, 3 should be 0. So on up to A2n also must be 0, right? So when we look at the n by n order matrix, all the other entries must be zeros except at the principal diagonal. Then only the principal diagonal will have non-zero entries and the rest of the matrix will have all zero entries. Such a matrix is called a diagonal matrix, and it is in short denoted by diagonal of A as the elements of the principal diagonal. Okay. Now there is another type of a matrix formed by principal diagonal, that is upper triangular matrix. Let's understand what is an upper triangular matrix. A square matrix where Aij becomes 0 whenever I greater than j. That means the row number is more than that of the column number if the element is 0. Then such a matrix is called a upper triangular matrix. Now let us see an example of a 3 by 3 matrix again. In a 3 by 3 matrix, how will be the entries? Yes, we will have A11, A12, A13, A21, A22, A23, A31, A32, A33, right? Now in this, whenever I is greater than j, that means whenever the row number is more than the column number. A11, no, here the row number and the column number are equal. A12, no, because here the row number is smaller than that of the column number 2. Similarly, A13 also, the row number is 1 which is less than that of the column number. But look at A21, yes, here the row number is 2 which is greater than that of the column. Then this element becomes 0. Will A22 belong to this? No, row number and column number are equal here. A23, does it belong to the requirement? No, because here the row number is smaller than that of the column number. Then A31, yes, this is also 0 by the condition. A32 is also 0. Now when you write such a matrix, let us see how does it look like. It would have A11, A12, A13, but here the element is 0, A22, A23, 0, 0, 833. Now if you look at the reason why we call this as an upper triangular matrix is this portion of the square is zeros. So the non-zero entries are there only in the upper portion of the square, right? That's why this is called as upper triangular matrix. Where the lower triangle formed is having all zeros, then such a matrix is called as upper triangular matrix. Now if we want to write a small example of a upper triangular 4 by 4 upper triangular matrix, right? That means this should have 4 by 4 entries in which the lower portion of the triangle must be having all zeros. So how will be the elements? 3, 4, 5, 6. But if you look at this element here, what would be the order of the element? Yes, it would be A21, second row, first column, where the row number is more than that of the column number. Therefore, this entry must be 0. Now from here onwards, if you look at A22, non-zero. Again, here the entry would be A31. 3 is the row number and 1 is the column number. Therefore, this element is 0. Here also the element is A32, where 3 is the row number and 2 is the column number. So 0. Now, is this an example of an upper triangular matrix? Yes. If you observe the lower portion of the square, all the entries are zeros. Then such a matrix is called upper triangular matrix. The elements to the left of the principal diagonal. Now another identification is this is the principal diagonal of the matrix. Then the elements to the left side of the principal diagonal are zeros, right? Such a matrix, all these elements are zeros to the left side of the principal diagonal. Such a matrix is called as upper triangular matrix. Now let us see the other way of getting the same, that is lower triangular matrix. Now here an element Aij of the matrix is 0 if I is less than j, that means the row number is less than that of the column number. Then such a square matrix is called as a lower triangular matrix. So how will be the lower triangular matrix of order 3 by 3? Yes, it will have elements entry A11, A12, A13, A21, A22, A23 and A31, A32, A33, right? Which identify the elements for which the row number is smaller than that of the column number. Yes, A12, that is 0, A13, this is also 0, A23, this is also 0. All the rest of the elements are either row number equal to the column number or the row number more than that of the column number. Then this matrix when expanded would be in the form A11, 0, 0, A21, A22, 0, A31, A32, A33. Clearly, if you look at what is the principal diagonal in this matrix? Yes, this is the principal diagonal of the matrix, and the elements to the right side of the principal diagonal, that is on the upper portion of the square, are all zeros. Then such a matrix is called as lower triangular matrix. That is, if all the elements to the right side of the principal diagonal in a square matrix are zeros, then it is called a lower triangular matrix. Now can we consider an example of a lower triangular matrix of order 4 by 4? Yes, it will have 5. Once you move to the right side of this, 5 is an element in the principal diagonal, right? 3, 2, 1. This is a square matrix of order 4 by 4. Now as we wanted a lower triangular matrix, all the elements to the right side of this principal diagonal must be zeros. That means the rest of the elements on the right side of this must be zeros. And here there could be any non-zero entries. Let's say 4, -2, 0, 1, 4, 2. Now can we call this as a lower triangular matrix? Yes, only the right side entries of the elements are all zeros to the principal diagonal. All the elements to the right side are all zeros. Then this is a example of a lower triangular matrix, right? Now another type of an important matrix is a scalar matrix. What is the scalar matrix? A diagonal matrix whose elements of the principal diagonal are all equal. So if you remember a diagonal matrix, how did we define a diagonal matrix of A of order say 3 by 3? Yes, it would have A11 element as a non-zero, A22 element, A33 element and the rest of all the elements are zeros, right? This is our diagonal matrix, which we denoted it as diagonal of, yes, A11, A22, A33. Now, in this diagonal matrix, what is the extra call required here? If the elements of the principal diagonal are all equal, that is, A11 is equal to A22 is equal to A33, then how will be the matrix now? It will be in the form A11, 0, 0, 0, A11, 0, 0, 0, A11. Such a matrix is called a scalar matrix in which all the principal diagonals are equal. Now say when we wanted to express 4, 0, 0, 0, 0, 4, 0, 0, 0, 0, 4, 0, 0, 0, 0 and 4. Is this a diagonal matrix? Yes. Except all elements in the principal diagonal, the remaining all elements are zeros. And the elements in the principal diagonal are all equal. Therefore, can we call this as a scalar matrix? This is when denoted as diagonal of 4, 4, 4 and 4. Yes, this is a scalar matrix because all the principal diagonal elements are equal. Now what happens in a particular case of a scalar matrix where all the diagonal elements are 1? Yes, a square matrix in which all the principal diagonal elements are equal to 1 and the remaining all elements are zeros is called a identity matrix or unit matrix. So when we are writing an identity matrix of order 3 by 3, how will be the entries? Only the principal diagonal elements would be 1 and other than the elements in the principal diagonal, all other elements are zeros. Then such a matrix is called as identity matrix, right? And this can be denoted as diagonal 1, 1, 1, right? So can you tell me how will be the identity matrix of order 2 by 2? Yes, it should have a 2 rows and 2 columns where the elemented 1, 1 and 2, 2 should be 1 and the rest of the element should be zeros, right? This is also denoted as diagonal of 1, 1. Then such a matrix is a identity matrix of order 2 by 2. This plays a very important role in the future calculations of matrices. When we study further about matrices, this identity matrix plays a very major role. Now, two important observations regarding an identity matrix is I is a scalar matrix. Right? Not only I is a scalar matrix, I is a diagonal matrix. Every identity matrix of whatever order, whether it is 2 by 2 or 3 by 3, it should be first a scalar matrix because all entries in the principal diagonal are equal. And it is also a diagonal matrix because in the diagonal, other than the diagonal elements in the matrix, all other elements are zeros. So every identity matrix is a scalar, diagonal, and having the entries as the equal entries as 1, then the matrix is a identity matrix, right? Now as we begin the algebra of matrices, which is a new entity of representation of elements, first let us learn about equality in the representation. When do we say two matrices are equal? When two matrices A and B are defined as collection of Aij's of order m by n and B is a matrix of collection of Bij's of order p by q. These two matrices are said to be equal. Two very important conditions. One is m equal to p and n equal to q. That means the number of rows in both the matrices should be same and the number of columns in the two matrices should be same. Now is it enough that I have two matrices of order 3 by 2 and another matrix B also of order 3 by 2? Then can I say they both are equal? No. What is the second condition? Aij must be equal to Bij. That means every element in Aij at the corresponding position of ith row and jth column must be equal to that of the corresponding element existing at the ith row and jth column in the second matrix also. Then we say the two matrices are equal. That means if we have an A 3 by 2 matrix given by X, Y, A, B, C and D. This is a 3-rowed 2-column matrix. And in a B which is also 3 by 2 matrix, if I have entries L, M, N, P, R and S. Now that both the matrices orders are same, then what is the second condition says? Yes, provided the element at the first place in the first row, first column must be same as the second matrix element in the first row and first column. That means X should be equal to L. Similarly, Y should be equal to M, A should be equal to N, B should be equal to P, and C should be equal to R, as well as D should be equal to S. Then only these two matrices would become equal, right? So entries should be equal at the corresponding position and the matrices order must be same. Then we say the two matrices are equal, right? Now as a simple example to establish, I have a matrix A defined as 3, 4, 5 and 6 and another matrix B is defined as X, 4, Y, 6. Now can you identify for what values of X and Y will these two matrices be equal? Yes, if A and B matrices are same, then first we should have the orders must be same. Yes, A is a matrix of order 2 by 2, B is also a matrix of order 2 by 2. Then after the orders are equal, the corresponding elements must be equal. If you look at the element at the first position, first place should be same as the element at the first position, first column. That means X value must be 3. Now the rest of the elements 4 and 4 are equal. Now again the element at the second row, first column should be same as the element at the second row, first column. That means 5 should be equal to Y, and then the element in the second row, second column are already equal. So if the two matrices are equal, then the value of X must be 3 and the value of Y must be 5, right? So important here, two matrices are comparable to be equal provided two simultaneous conditions are satisfied. First, the number of rows should be equal in both the matrices. So for the matrices to be equal, the matrices must be of the same order and the corresponding elements at the corresponding positions must also be same, right?